palestras sobre o tópico de criminologia e matemática, ou seja, o quanto a matemática pode impactar na criminologia. E quando eu falo matemática, eu falo, evidentemente, no sentido amplo de matemática e estatística. Este evento ele é o resultado de um trabalho de alguns anos que o grupo do Laboratório de Análise e Modelagem em Ciências Matemáticas vem fazendo, e nós estamos trabalhando com projetos relacionados a aplicações, e hoje nós temos o prazer de iniciar esse evento com o professor Jorge Mateu, da Universidade de Jaume I, de Castellón. Ele vai falar para nós sobre modelos preditivos em modelagem de crime. E o professor Jorge Mateu é um dos grandes especialistas da área, com um grande número de publicações, e está aqui no Rio por alguns dias, a caminho do Peru, onde tem desenvolvido vários trabalhos no Peru e na Colômbia, no estudo de criminalidade. Então, eu queria agradecer a presença do professor Jorge Mateu. As palestras serão, em princípio, em inglês, para que tenha um acesso a um grupo maior. Porém, as perguntas, se quiserem, pode ser em português, espanhol ou inglês. Muito obrigado, professor Jorge Mateu, pela sua presença. Graças por sua presença cá. Por favor.
Well, I don't know if I should start in English or I should start in Spanish, but just for those of you that they come from a country that speaks Spanish, estoy muy agradecido de estar aquí. Gracias a Jorge, gracias a Vences, gracias al IMPA por haberme invitado unos días y conocer el IMPA y conocer esta pequeña parte de un instituto de matemáticas que siempre tiene unos fundamentos sólidos en la sociedad. Entonces estoy muy agradecido. And then turning into English, and of course everything is in English here. I will speak in English, but if you have any particular questions, just you can ask me in Portuguese or in Spanish. Right? Good. So this is just a kind of very general overview of what we've been doing in the last 3-4 years. I belong to a department of mathematics, and 4 years ago, someone from the police came, they knocked at the door and said, we have this problem, we have this data, there are lots of things that we know that science can help us, and we don't know how to deal with these problems. So we come here to a department of mathematics to ask for help. At that point, I'm talking about something like 4 years ago, at that point I said, oh, mathematics have to do with crime analysis. And then I have a thought and said, yes. At that moment, we were analyzing forest fires and earthquakes. And we were doing stochastic modeling of forest fires and earthquakes. And then I said, oh, maybe crime data has something to do with forest fire. The way a fire behaves has similarity with the way a crime evolves in space and time. And it has some similarity with the way earthquakes evolve in space and time. So at that point, we changed our mind, and we start thinking of how to predict crime data using spatio-temporal stochastic modeling. And the story started something like 4 years ago. So this presentation is kind of predictive stochastic models for crime, modeling the dynamics of crime, because crime is something evolving in space, evolving in time, with interactions between space and time. So there is no way to deal with crime data just ignoring time, just considering snapshots in time, so spatial things. There is no way with dealing crime data only in time. The whole thing is dealing with crime data in space-time, what it's usually called spatio-temporal data, right? Let me start. I mean, this is kind of, I don't know, I have something like 45, 50 minutes, but let's see how the seminar evolves. But the thing is that I'm starting with some real data analysis to motivate the problem. And then I will focus on two big data sets that we've been analyzing. One is coming from Colombia in Bogota. The other one is coming from my local city, Castellón, Spain. So I will start with some data from these two places, and then I will move to the more technical and methodological details with some results and these things. Fine. So let's, well, this is, when 4 years ago we started thinking about these things, I revised the literature, and I revised which institutes worldwide, everywhere in the world, they were dealing with kind of multidisciplinary, let's say, kind of different points of view, different perspectives to deal with crime data. And then we realized that there was this UCL, University College London, the Jill Dando Institute of Security and Crime Science. And when you Google that and you go inside this institute, you realize that there are geographers, there are statistical people working in that institute, there are psychologists working in that institute, there are architects working in that institute, a very interdisciplinary work over everything focused on dealing with crime data. Because crime data cannot only be dealt with mathematics, with statistics. You need the input from psychologists. You need the input from many, many, many different areas of science. And this institute is kind of an example of what should be done if you really want to deal with crime data. So this is, I mean, it's nice if you Google into that institute. There are lots of things going on there, and it's a clear, motivating example of institute with crime data. But going back in time, the real initial way of dealing with crime data was in 2011 in Los Angeles, in the States. There they realized that crime analysis has lots of links, common things with earthquake analysis. And they were experts. You know, there are lots of earthquakes happening in that area of California. They were experts in earthquake modeling, and then realized that from a mathematical point of view, dealing with earthquakes, it's basically the same thing as dealing with crime data. And they started to analyze this crime data using their methods from earthquake modeling. And they, well, at that time, we were talking about something like almost 20 years ago. Computers, they were not so fast, they were not so strong as they are right now. And of course, this area where big data is being analyzed right now, it's kind of, we need strong computers, but when they started to analyze this crime data, they reduced the numbers of crimes in Los Angeles just using this kind of spatio-temporal stochastic modeling. That was at the very starting point of the area of dealing with crime data. These three, I'm sure, I mean, I don't know if there is any policeman here, but they really like these three words. They should be smart, they should be effective, and they should be proactive policing, or they should do proactive policing. They don't want to be reactive. In general, the police, they want to be proactive. So trying to make things in advance rather than having an action after it has happened. And this is the change, the big change of mind of the, let's say, European police at the moment. And the only way to be proactive is knowing in advance what will happen. If you know the probability that something will happen, you can react before it will happen, and then you can just be proactive and not taking any action after something has happened. And just have a look at this graph. This is a kind of summary of what we are doing with the police. I mean, we have, we get the data collection. We have this kind of data fusion, which is, I mean, there are lots of data coming into play, and the data, it's coming in very, very different formats. Some of them are geographical-based things. Some of them are just cumulative numbers of something. Some of them are geoprocessed by something. So there are lots of possibilities of data coming into play. And of course, the very first thing is you have to put everything with the same format, so data fusion, and then analyze your data. You analyze your data, you have kind of prediction of your data. This prediction has some intervention on the police operations. And then, when you have the intervention with the police operations, of course, that has an input on the criminal response, with the idea of reducing that criminal response. So once you altered this criminal response, again, you have data, again, you analyze the data, and again, and you go into the loop. That's the big thing. Data, analyzing the data, going to the police practice their own play on that. You reduce the data, the criminal response to that thing, you come back with new data, and you go into the loop. Fine, so let me just show several examples that we've been working with in the last years. This one has to do with traffic accidents in Houston. It's not kind of criminal data, but traffic accidents, it's something important also for the police. And the nice thing here is that this is Houston, the city of Houston. You can see clearly here a network, which are the streets of the city, and of course traffic accidents are happening on the streets. And that makes a big difference with respect to the plane. It's not the same working on a subset of R2 than working on a kind of the support being a network. The distances are non-Euclidean, and you have lots of geometry things. Many things are changing here, but this is one big thing. In this case, working with vehicle traffic accidents in one city. This is again the same kind of thing, traffic accident, this time in Perth, in Australia. Same kind of thing. This is down in Colombia, in Medellin. Here we have traffic accidents with 3 different outputs. The one on the left-hand side is a kind of property damage, right? The one in the middle is person injuries, so traffic accidents with a consequence of having injuries in the persons. And finally, on the right-hand side, unfortunately, there is a few of these cases because it's fatal, it's with death, people dying on the traffic accident. So we have, the general thing is traffic accidents happen on roads, happen on a network, with, of course, 3 different outputs from these types of accidents. That's Medellin. This is in Mexico, in the city of Neza, which is really border with Mexico DF. Well, this city, these are car thefts. And the police recorded the number of robberies, of car robberies, and those that were recovered. Of course, the subset of the set of recovery cars is a subset of the overall set of robberies, right? Not all cars that is being robbed, is being theft, is being recovered. And the police, they came to us, and they said, could we have a probabilistic model so that if I tell you where this car has been theft, where this car has been robbed, tell me with which probability that car will be recovered and where in the city. If it's been recovered and where the space in the city. And this is something I will tell you about. There is one paper that we've published based on these probability things that is nice. I mean, they just have probability and kind of let's say, color maps indicating probability risk of if this car is being, was here and was robbed from here, there is a probability that it will appear up there. It's nice. This is well, this is the city of Neza. It's been divided into the north of the city and the south of the city, and the blue dots are the car theft locations, and this one on the left-hand side is the recovered locations. I will tell you more about this. So let me tell you something about the data in Bogota. Well, in Bogota we have, that's in Spanish, homicides. That's one thing. This is just a temporal, so it's just number of homicides per day in the last something like 6-7 years, right? Homicides. Then we have the time series, so counting the car robberies on the left-hand side, and on the right-hand side, the motor vehicles robberies. In the city, Then we have robberies to commercial places in the city of Bogota, and robberies direct to persons, to people just in the streets, and they are robbed in the streets, so we have this time series. You see, there's something going on the last something like 2 years from 2016 in terms of robberies to person, and that's lots of things to do with cell phone robberies. The previous things were just time series, just counting. Now let's go to the spatial distribution of these things. So these are the homicides, the spatial distribution in Bogota of the homicides. The spatial distribution of robberies of cars and robberies of vehicles, of motor vehicles, and the spatial distribution of robberies to commercial places and robberies to person. You see, robberies to person, it means that everywhere you are, you will be robbed, in some sense. Of course, this is not that true. I mean, I've been lots of times in Bogota, and it never happened to me. Maybe I'm a lucky person, but it never happened to me. The thing is that there, it's a kind of condensed information of the data for the last 7 years, so it's kind of good. And then we have the covariant information. I mean, it's not just that we have only locations and times of the particular crime, but we have additional information, and this additional information comes in form of, for example, distances. This one on the right-hand side, this is the distance from each event, so from each place where something has happened to the closest, this is place of construction, building places. Or just have a look at this one. So distances to water places, or distances to pharmacies, distances to locations where we have schools, secondary schools, universities, or IPS, distances to health centers, IPS. Why distances? Because I mean, I think there is no more here. Ah, yes, this one on the left-hand side. This is transport. Transport means, you know, there is this big bus which is called the Transmillennium, which crosses all Bogota in all directions. And there are these bus stops. And there are hundreds, I should say, even at some point, at some moments of the day, thousands of people just waiting for the bus there. That's the perfect place for people to rob people, for example, to rob the persons in the queue, right? So it's nice having the distances to each one of these bus stops. Just a kind of covariant, something that can be helped in terms of predicting where and when something will happen. And also distances to parks in the city. And much more, I mean, here there's only. And then, so I've told you locations and times, I've told you covariant information in space, but there is also covariant information in time in terms of meteorology. That's precipitation. Maybe if it's raining, there are few people just walking in the streets. Maybe if it's raining, the criminals are not going in the streets, or the other way around, whatever it is. But it might be that the prediction, the precipitation has some role on kind of robberies, right? So also this kind of meteorological information, additional meteorological information, comes into the model. And now let's go to my city. To my city is something like only 200,000 inhabitants, so nothing compared to Bogota. But the nice thing here is that it's a very quiet city. It seems that nothing is happening, but for the police, it's very important that even if that's an example of a quiet city, something is happening there. And if the models are doing a good job in predicting the crime with a city that it means that nothing is happening there, then the model will be nice for any other more complicated city. So the city is this one. This one on the right-hand side is violence. So it's you see these yellow points. This is the city of Castellón, and the yellow points, again, something happening on the streets, and the yellow points are just the locations of calls to the police based on violence. And on the left-hand side, you see this is for 2 years, 2012 and 2013, the number of calls for these 2 years. We also have this one, which is calls in terms of noise in the streets in terms of whatever, crime in the streets, kind of molestias in English. I don't know the word in English, but molestias in the streets, right? So again, the calls to the police based on that. Harassments, yes. So this is just, again, X, Y, and T. But then the data, I've told you in that kind of scheme, one point was data fusion. Because in some cases, the police, they have this kind of additional information. For example, just they divide the city into small districts, and they count the number of events within that district. So they don't have particular locations, but they have a number of cumulative counts of something happening there, and then they have these sort of things. Just the city divided into districts, and within a district, here is kind of color map. We have this counting of, and they have this. For example, they have distances to pharmacies here, and they have even an economical thing in terms of this is the value of the building or the houses. So kind of economical index saying, well, which part of the city is richer than other parts of the city. Fine. So this is kind of different types of data. I will focus on these two, on Bogota and Castellón, but you see traffic accidents in many places of cities all around the world, and so kind of a big range of possibilities to be analyzed. So let's go a little bit into the mathematical thing. Well, let's start with this thing. What is a statistical model for you? Well, a statistical model should be this kind of triangle with the three corners of the triangle indicating three things. Statistical model should be a device to answer questions. At the same time, it should be a bridge between the scientific theory and empirical evidence. And finally, it should be a framework to enable principal inference in the process of uncertainty. And that's the big thing, uncertainty. And that's the difference between stochastic and physics. Sometimes the students, they ask, what is the difference between physics? I mean, if I have a law, a physical law. I apply the physical law and I have this output. So what is the role of statistics? What is the role of the stochastic model here? What is the difference with physics? The difference is uncertainty. With the statistics, we can model uncertainty in the data. And sometimes the uncertainty is the devil. The mathematicians, they say, the devil is on the details when you just try to prove something, right? Here, the devil is on the uncertainty. There are lots of things, especially with crime data. I mean, crime data has to do with the behavior of people. And you cannot control completely the behavior of individuals. That comes into the uncertainty thing. And you have to model, you have to, in some sense, to compensate for that. So that's the three things here. So let's start from the basic thing. And the basic thing is assume that there is nothing happening there. Assume that this collection of events in the region, they just follow what is called a complete spatio-temporal randomness model, which means there is no, let's say, a structure in space, there is no structure in time, there is no interaction between space and time. You just have a random collection of points, of events, randomly distributed in your region. This is the basic, of course. I mean, we have our idea is to reject that thing, because if these things, if this model is the base of one type of crime, you have to go to the police and say, no, just do nothing. You cannot control these things. Nothing can be done here. So, but this is a very starting point, this thing here. Fine, so let's try to modify that a little bit. And then the second simplest model is the Poisson, which is the random model, but inhomogeneous. Inhomogeneous means that everything is random, but the locations of your crimes depend on external covariate information. But given condition to that external covariate information, two crime locations, they are independent. That something, if one crime happens here and another crime happens 2 meters apart from where I am, it depends only on covariate information, nothing on the spatial or temporal structure. That's what it's behind this inhomogeneous Poisson process. Right, so basically the number, this capital Y, the number of crimes in W, which is the spatial region, times T, which is the temporal region, follows a Poisson distribution with one particular mean, and the mean is this double integral of this lambda. Lambda is called the intensity, the spatio-temporal intensity, which is nothing but the number of points in space and time per unit volume. Fine. And then let's go to the third one. And this third one is the basic, not the basic, is the base for the further development. And this third one is the Cox process. Let me just go here. The Cox process says that events, they happen on particular locations in space and time according to a particularly homogeneous spatio-temporal Poisson process, and this is the difference, with a stochastic intensity, this capital gamma of xt. And the clue, the difference is here, this Cox process depends on a stochastic spatio-temporal intensity. And all the mathematical development you will see that is just based on this capital gamma here. In particular, we assume, to make mathematics simpler, that this gamma, capital gamma, is the exponential of S, where S is a Gaussian random field. I don't know if you've a little bit, you've read something about random fields, and well, the thing is that what we observe is just the locations of crimes. What we don't observe, so the latent process is something hidden, which is a stochastic spatio-temporal random field. Of course, what's happening underneath reflects on the locations of the events. But we don't observe this kind of hidden process or latent process, we don't observe S. And we have to make inference of S just observing the locations of the events, of the crimes, right? And that's the big thing here. And then the basic formulation is this one. The number of crimes, this capital Y, at a particular spatial location I, subindex I, and a particular time interval Tj, given condition to the latent process, is given by a Poisson process with that particular mean value. And the mean is the double integral in space and time of the stochastic process, capital gamma. And so we need to make further assumptions here. And this one, I'm sure that Wenceslao is now thinking about separability between space and time. It's coming here. Because this gamma, we can assume that can be decomposed into two parts. One big part, which is mu, that's a deterministic one. There is no stochasticity there. And the deterministic, this mu of xt, is decomposed here in two terms. One is something depending on space, the other one is something depending on time. So all covariates, those that are spatial covariates, they come into lambda. Those that are temporal covariates, they come into mu. And lambda times mu, they provide this deterministic term. And the other part is this R, this exponential of S, which is the stochastic part. Now the question is this right? Because here we're assuming that space and time are independent. Because we are saying that mu of xt is split into mu of t and lambda of x. And what happens with interaction? Don't worry, the interaction comes into R, into the stochastic part. It's like, let's do simple things in the deterministic part, and the rest, the residual of that thing, they will go into the stochastic part, and then we will take care of the stochastic part later on. That's the nice thing with this development. So, well now, that's fine, so it's half an hour. Okay, so now there is some development. I mean, it's not important, it's just to give you an idea of different things that we can do here. For example, the first thing that we can do here is that if we go back to this expression, if this lambda capital lambda is decomposed into these three terms, then we can go into the basic model, and then this is being decomposed into these three terms. And then you can do just what depends on one thing, what is constant with respect to the other. So finally, the number of crimes in space and time, it's a Poisson a random variable which has this kind of a mean term. And then it comes the question. So, for example, the data has continuous time or discrete time. So the time can be considered a continuous variable, or the time can be considered a discrete variable. Depending on that, then we can do some more mathematics, some more developments here, the expected value of crimes in space and time, given by this. If t is discrete, the expected value is given by this. We can obtain the covariance structure between number of crimes in space and time with number of crimes in another space and different time, and then we can just consider this kind of development here. And we can do lots of things. For example, someone or the police could be they could say, I'm not interested in what is happening day by day or even hour by hour. Just tell me what's happening in the whole day. After one day, I'm recording, accumulating at the end of the day. Tell me what's happened. That's fine. So then we say that we accumulate, we have this thing, and then we can just do a kind of formulation for the accumulative events in time. The covariance and this thing. So, you see that the stochastic term is always there, and it's hidden. We cannot observe that, and that's the devil, as I told you. We have to go into the spatio-temporal structure of the Gaussian process, which is hidden, which is a latent process. How can we approximate that? Well, assume that there is a correlation in space and time, and assume that this correlation of the processes is given by a function that depends on the spatial distance and the temporal distance. And again, we have a discussion here. What is a spatio-temporal distance? Or in other words, do you think that the spatio-temporal distance is just the product of the spatial distance times the temporal distance? Or it is just the Euclidean distance into R3? So you go to R2, the Euclidean distance in space, well, you consider one extra, let's say, component, and then you have a Euclidean distance in R3. Is that right for space-time? And the answer is no. Time is not just a third coordinate in space. I mean, you can do 3D Euclidean distance if the third coordinate is just the volume, for example. You have x, y, and z. That's fine. But if the third coordinate is time, time does not behave in the same way, in the same manner as a coordinate. So you need to look for appropriate spatio-temporal distances. And that's another question that I will just leave open here. Fine. So what if we can find a model that provides this kind of probability? The police is interested. If the police comes to the office and say, well, I mean, we cannot, with the number of policemen that we have in the streets, we cannot go to every place. We have a threshold, and the threshold is, if something is happening, I mean, if we have more than 10 events happening in the same place, then we can act. If there is only 1, 2, 3 events, I'm sorry, we cannot go there. So there is a threshold, this C here, that this kind of, from that threshold onwards, the police will act. From that threshold beneath, they don't move in some sense, right? And they want probabilities. So tell me with probability, this stochastic process has greater will be greater than the particular threshold. And this is the kind of maps they want. Fine. So now, to approximate this thing, we go into a statistical inference. And well, the thing is that if we go to the likelihood function, given the parameters, this likelihood function is the expected value with respect to the latent process of this quantity here. But this quantity here, it has a problem here in the denominator. This integral of exponential of s times lambda It's not known. In fact, it's nice to see that it is not known, but what is this? This is the expected value of this term with respect to the distribution of lambda. So you cannot obtain the integral in a direct way, but you can observe that this integral is the expected with respect to lambda, the distribution of lambda, of the exponential of s. And if you assume that thing depends on this quantity, so if you assume that, then you can get an approximation to the denominator of the previous expression. And if you obtain this thing, then you can approximate the process S with what is called a low-rank stochastic process. Low rank means that whatever you have in space and time, if you have 100,000 locations in space and you have 300 locations in time, there is no need to observe S over all these combinations of spatio-temporal locations. You can obtain a kind of low rank. Just tell me, select some nodes in space and time and evaluate S over these nodes. And this is exactly what it's been doing here. It's been doing here, this kind of, let's say this V here are the nodes, and with just kind of low rank approximation, we obtained a corresponding approximation of the process S. There is another thing here. This S depends on these B's, and B's are mutually independent, normally distributed random variables. This is a first approximation. Now we are working on extending these things by using dependent normally distributed, not independent ones. But that's something that will happen in the future. And one more thing, this thing here. I'm sure that some of you or most of you know about these kind of stochastic processes, the Ornstein-Uhlenbeck process. If we think of them to model the process S, then we have this nice expression here. S can be normally distributed with this mean value, with this, let's say, variance covariance matrix. And it's nice because you see, it depends on space, it depends on time, and then here, the space is here, time, particular time where you want to evaluate your process, and then we can have forecasts of this stochastic process. For example, if we observe time until T2, which is the current time, and we're going to predict this till to k times forward, then we just have to focus the Poisson intensity based on this. And there is more. We can evaluate the expected value of the forecast. We can evaluate the variance, the variability of the forecast. So every time we provide a kind of, let's say, probability map of the forecast, we have the corresponding variability map of that forecast, so that the police can say, oh, that's fine. I mean, something will happen. There are 3 events happening with a particular probability, but the variability of these 3 is minus plus 2. So it could be 5, it could be only 1. And then they have the decision on their hands. That's fine. Well, then we use MC, and that's. So let's go into the practical thing, right? As I've told you, 2 years in this small series, 2012 to 2013, these are calls for violence and robberies in the city of Castellón. And for those of you, this is Spain, and Castellón is basically here on the Mediterranean area, small city around here. And fine, what is happening with the intensity? So remember, have in mind that this capital lambda has 3 terms. One term is the spatial intensity, lambda, this one here. Another term is the temporal intensity, and the final term is the latent process, stochastic spatiotemporal process, right? So in terms of lambda, we use just a kind of generalized additive model for various, let's say, spatial covariate information that we have. Distances to pharmacies, distances to here, distance whatever. This kind of spatial covariates that they play the role on the number of points happening on the space of the city. And this is the graphical representation. That's this is the typical hotspots map, but it's not a hotspot. I mean, the hotspot is just a representation. I mean, behind this thing, we have the corresponding intensity evaluated with this kind of gamma modeling strategy, this thing, right? So this is only intensity in space. Now we go into the temporal thing. So, so we have the temporal here, the temporal distribution, which is the black lines here and here, and then this blue line is just the corresponding intensity, is the estimate of mu of t, the intensity, the temporal intensity estimation, right? And you can see, well, it's a good fit, but it's not perfect. I mean, all these peaks here, they are not being accounted by the general temporal trend. Peaks here or peaks down here, they are not being accounted. That's no problem, because remember, I mean, everything that is not being accounted in the deterministic part, it goes into the stochastic part. So let's try to do our best in that deterministic term, and everything that is not being accounted for there, then it will go to the stochastic one. So let's go to the stochastic one. And then remember, here there are lots of things to do, and this is the more complicated part. It's a latent process. We don't observe that, and we try to approximate with this stochastic part S. So let me just go a little bit quicker here. This is just not important. The estimation of parameters of the stochastic part. And the nice thing is that once we estimate the parameters, we're able to fit this kind of Ornstein-Uhlenbeck process here on this stochastic term, and then we can predict, so we can do forecasts in time for this stochastic process. And then we get this thing, and this is what the police gets. I mean, of course, everything is hidden to the police. I mean, the police, they don't care about mathematics, they just care about this. And what they care about is this kind of map. Prediction intensity for violence robbery with a risk over 25%. And these kind of maps, they want these kind of maps hour by hour. And if it's possible, on real time, because they have this kind of iPods in their cars of the police, and they put all the data there, all the cars, they go to a central, let's say, computer. So every hour, the computer receives all the data from all the cars running around the city. And then the model is being refitted, recalculated with the new arrived data. So these prediction maps are being kind of being rebuilt, and they have new forecasts every hour with new data just arrived from the previous hour. And this is what the police they wanna have. That's for Castellón. What happens with Bogotá? The same kind of thing, with, of course, different particularities. For example, the intensity here, the intensity in time here, mu of t, you see it has a kind of periodic behavior. You can see that everything moves around a kind of periodicity around every day of the week. And then you have a kind of, let's say, a smooth function of t, of time. So you have the periodicity, and then you control the periodicity adding kind of a smooth function of t. But we also have here, you see, this delta d of t. This delta d of t is the effect of the day of the week. The behavior is not the same if it's on Mondays, if it's on Fridays, if it's on Saturdays. So the day of the week has an effect on the particular model. That's for mu, for the intensity. Well, that's kind of thing for the homicides, for the robbings of cars, robbings of motorbikes, for robbings in commercial, robbings in person, and then the day of the week, which day of the week they have a significant, let's say, significant role on the intensity, temporal intensity model, and also the month where we have this thing, and the covariance information. That's for time. For space, the same kind of thing. I mean, we have the corresponding distances to water, to pharmacies, to transport, to parks, whatever, and then which of these covariant information they have a particular significant role on the spatial intensity. That's important. And prediction. That's Bogotá. And that's next hour prediction. So tell me, what is the prediction, the probability of the risk, it's called risk, or probability that something is happening on the next hour. So here is for homicides. I mean, I don't know if you can see, basically there is one point here. I mean, we are lucky in the sense that homicides are kind of rare events, but there is something here. In the next hour, there is, you see, kind of high probability that a homicide will happen here, in that part of the city. But have a look at car robberies. Oh, police, they have to act here, because you see, on the next time, on the next hour, lots of possibilities happening here, here, in these areas of the city. You see, in the green part of the probability, which is close to 1. Then, of course, there are some yellow, some oranges. And then the police, they have to act against this thing, right? Again, in this case, for commercial robberies, I think there is one happening here and the next one happening here, one happening over there, one happening over here for the next day. And then that's for robberies to persons on the next hour. Again, with probability 1, there will be some kind of robberies in all these areas. Right? Fine. Then, I mean, the base of all these things is just this kind of log Gaussian Cox spatio-temporal Cox processes. And regarding this thing, what I'm saying is that we have a Poisson process where the probability that something is happening depends on space, spatial covariates, depends on time, temporal covariates, and depends on a hidden spatio-temporal stochastic process. These three things together, they form the basis of the probability that something will happen. But there are alternative possibilities to here, and these are some alternative possibilities. I have 3 here. I named 3 of them here, but there are more than this. These 3 here are just based on, I'm sure that you've heard about this Hawkes type point process. This is another type of models. They're called Hawkes types. And Hawkes, it's an earthquake model. It does not come from crime data. It comes from, if you go to the literature of earthquakes modeling, you will see the Hawkes process just, they're born in that area. And they've brought into the crime data analysis. So this is just a recent paper published this year in Royal A. Then we have this kind very connected with Hawkes process. We have the self-exciting processes. Again, very much connected with Hawkes processes. There is a very nice paper last year in Statistical Science, kind of review paper for these processes. And this thing I've mentioned on car thefts with origin, destination, and recoveries, which is again published this year in Royal A. Why am I mentioning these 3? Because these are 3 examples of alternative models using point process strategies, stochastic point processes strategies, that they deal with spatio-temporal prediction of crimes. The nice thing is that they take ideas from earthquake modeling into the crime thing, into the crime data. And at the end, from the mathematical point of view, there is not a big difference. Of course, there are differences in terms of adaptation, psychological things on crime data, and some other things. But if we go into the, let's say, the formalism, it's basically the same thing. I don't have time to, I had the PDF of this paper, and of course I can share with you if you want to have a look at them, but I think I don't have time to go into these three papers here. In any case, the important thing, and I'm finishing with this, is this kind of real-time surveillance in space and time. Real time, we are heading to that. We're in the area of big data. We're in the area that we, the police, they want quick things. I mean, the police that doesn't want to knock at the door of a scientist saying, please bring me, provide me probability maps of forecasts. And you say, that's fine, but it will take 1 day to run. No, I cannot wait one day just to see what will happen. I need quick things. And quick things means real-time surveillance in space and time. And that's important thing. So it's a kind of computing challenge and yeah, and many other things. So thank you very much for your attention.
Thank you very much, Jorge Mateu, for this very nice talk. This is obviously very, very important talk and very important work on the topic. And I'm going to open the floor for a few questions. And we are going to stay here the whole day, so hopefully during the break, people can also ask further questions. But let's go for some questions now. So please.
Thank you. The saying, as Jorge told, is very good. Told, congratulations, I enjoy a lot. As you know very well, we have a long history working together. And one technical question. You say, well, I will use, in a Latin way, Poisson process. So they use log Gaussian process. And you say, well, then I avoid the problem of consider or not the separability. Mm-hmm. But I think that you really translate the problem of separability to the covariance structure in the Gaussian process. So then you have again the same problem. So then what do you suggest for prediction? Which kind of covariance structure for the spatio-temporal process? Because the problem is there again.
Yeah, that's fine. That's a nice question. But you know that we have the deterministic term is something on the spatial point process methodology. Mm-hmm. And the covariance structure of the latent process is a kind of random field geostatistical problem. Yes. And there we have lots of non-separable covariance families. There is much more richness in there than in here. Mm-hmm. So translating the problem into there makes things a little bit simpler.
But you have again the problem of goodness of fit of the correct covariance structure. There.
Exactly.
And another question, last one. Prediction, of course, as you know, is a very crucial problem here. And then the question is, I am giving different weights using hotspots, because I can create a hotspot with density estimation. Mm-hmm. There are a recent paper, kernel density estimation with Twitter, yes. For example. What is the way of compare the behavior of the different ways? Because if I am given hotspots using models or using only the data, what's really the better way? How I can compare in the language of hotspots?
That's a methodological problem, because hotspots can be considered kind of object, stochastic object. And then your question just translates into how you compare stochastic objects. Exactly. And that's a completely new area. Mm-hmm. It's not easy, but of course it's possible from this stochastic geometry part of the spatial statistic random sets. You can do something there. Yes.
Okay, thank you.
Well, thank you for the very nice talk. I have a question that perhaps pointed towards the future of this work, right? Which is presumably when you have real-time predictions, there will be real-time interventions, and there's gonna be some response to the interventions, right? Do you have any thoughts on how to address that?
Yeah, and that's what we are aiming at. I mean, the thing is that this is trying to reduce crime events, right? So the police are taking this to be proactive and trying to reduce the thing. So what we have is right now we have implemented a kind of, this is what we have so far. Now the police is reacting based on these probability things. Now we're in a period of 1 year period where we're receiving new data and comparing the last data compared to the historical one. There should be a reduction. Based on that reduction, then we can implement other programs saying that that's fine, that it's kind of the model has provided a good forecast because the police has been able to reduce crime. But there is one latent question, which is you will never know, well, I don't know if never, you will never, but in some sense you never know if the reduction of crime is basically done because of the model fitting and the forecast based on the model, or because the police, in some sense, they've learned the process and they are better than before. But in some sense, at the end, the output and the aim is this reducing crime data.
So, do you think there's a chance that perhaps surely the spatial patterns will change, and hopefully the intensity
That's right.
of crime will go down everywhere, right?
Mhm.
But there could also be other kinds of reactions by criminals who kind of, try to evade the current hotspots and they'll go to other places. And do you see that happening? I mean, is there any pattern in the present data that shows that this is happening somehow?
That's happening because the thing is that when police are acting on one particular area of the city, you see that there is a reduction of that, but the reduction may be because the criminals are not acting there. They're moving to some other place of the city and acting somewhere. And this is something we're analyzing with something which is called trajectory patterns. This is a new thing again, where you control, the movement of persons, in particular of criminals, going around the city. And then you have the origin, you have the destination, you have kind of GPS where they're going, from where and to where, and you are taking this information of movement into the model.
Thank you.
Well, congratulations for the talk. It was really good and instructive. My question is, once you're making these, you are refreshing your estimates in order, for instance, to know on a daily basis the crime statistics. How do you can deal, for instance, with the fact that once you're making the estimations, you may have shifting patterns of criminality. For instance, criminals can be moving around the city. And then you should also be looking more closely to the most recent data. So how do you make the cut on the time window in order not to look as much as to past data? Because if you're considering, for instance, a larger window, you may be losing the most recent information, and also you may be delaying the time you have to act.
Right. Yeah.
So how do you make this time cut?
Well, the thing is, that's why I've said several times, real-time, let's say, surveillance. And when we say real time, is that there is no time window, and the time window is been moving every hour. So the thing is that you feed the model up to right now, but then 1 hour later you have new data, and then you use this new data to feed the model. So in some sense, you are not cutting the time at any moment. You just you shift 1 hour later, all in a continuous way.
So you analyze our data in order to...
That's right.
Okay, I got it.
So thanks for a very nice talk. Here in Rio, and I think there's many other examples in cities, you have two types of crimes. You have some crime that comes from organized crime schemes, traffic, even we can say political sometimes, and crime that's more, not necessarily small amounts, but little theft and everything. Can you somehow, you could address that, could identify crime that comes from tighter criminal organizations and try to understand that? So to think, is it that possible?
Yeah, well, it's...
What's your thoughts?
Yeah. You've seen that the type of crimes that we've analyzed in, let's say, in Bogota, which is a place where everything is happening there, right? Well, everything, but many things are happening there. But the thing is that we are not touching kind of particular crimes. There are some crimes where, let's say, the event behavior, the human behavior of the criminal is so important that the uncertainty degree is as large that the model really cannot fit the thing. So let's say that this works for homicides and this kind of robberies, which is fine, but maybe some other types of crimes which have to do with drugs or whatever, maybe they're a little bit, you have to go deeper into the modeling of these things. But the model is fine. The only thing is that you have to readapt to the particular behavior of one particular crime.
Well, that's fantastic talk, fantastic questions, lots of issues to discuss. Unfortunately, we have to move on. So I'd like to thank Professor Jorge Mateu once more. Thank you very much, Jorge, for this fantastic talk. So we just have time to adjust, and we'll